Click the bell icon to get latest videos from Ekeeda.
Hello friends, today we will discuss about the decomposition using the functional dependencies. We will now know that what are the functional dependencies that we can preserve while decomposing it, and the decomposition using notations and the features. And next we will know what are the BCNF, the 3NF, the 4NF according to the functional dependency changes using the redundancy losing. First, going for decomposition, we need for the preserving functional dependency. Well, functional dependency is a predefined rule to the relational schema so that some parts or some conditions need to be satisfying for a decomposition from a larger database to smaller databases. In any number, it can be done until and unless the dependency is being preserved or satisfied. Now, before going on for examples, we should know what are the notations that we mention while having the decomposition rules. First, we use that R or small alphabet as a relation name followed by the braces in the capital R as the set of attributes. So we define a relation R with a set of attributes capital R in it. For other notations that we can use capital R as a relation name, but we stick to some distinct portions of the notation so that it will not get mismatched or mixed up, that when I am referring to the set of attributes and when to the relation name. So for my example, I am using small r as the relation name and capital R as the set of attributes. Now the capital K is denoted to represent the super key of a relation R. So K brackets by R, that means that K is the super key of relation R. The next is the real names for attributes. See, when I am defining an instructor relation, we should use in small letter instructor as the relation name, so as to give the information to user that this relation is for storing the information about the instructor. Now, as a relation can contain a number of tuples or records in that relation R, so that tuple or a particular record belongs to the instances of R. So we record the tuple as an instance of R. So these are the notation that we need to follow or will follow in our functional dependency preservation and composition. Next, we will know about the keys and the functional dependencies on the decomposition. As we say that there can be some conditions based on a structural design by the database designers or for the end users. Now, if the keys or the conditions are being instructed from the end users, it is known as legal conditions or legal constraints or legal dependencies. So this type of dependencies are mainly user oriented and can be defined by the user. Say for the following dependencies that we are preserving. ID will be the primary key for the student and instructor both. So we can refer to any student by their ID. Also, we can refer to the instructor by their ID. So it is not the designer who is giving such constraints. It is from the user end that who is mentioning. Second one is can have the student and instructor only one name. That is no first name or no last name. The user is doing this for the purpose or the sake of making it a simpler way. So the student and the instructor can have only one name. Each student and instructor can be related to only one department. So in like this one name, we can also do the one department to student and instructor. Now we can say that each department has got a single budget and has got a single building. So each of the department will be taught in a single building and the building has got only one budget. So the department is related to the budget as well as the department is related to the building. So these constraints are known as legal constraints or the user-defined conditions that we can put as a functional dependency while decomposition of the larger schema into two smaller schemas. Now let us talk about keys on a functional dependency or a relation. When we talk about keys, that means the uniqueness that we can give to a relation or a record in a relation. So we can talk about a super key as a set of attributes if that combinedly uniquely identify a record in a relation. So in terms of the formal definition, we can say now, if T1 or T2 are tuples of a relation R that is consisting of a set of attribute capital R, then we can say that T1 if not equals to T2, that means if two tuples are uniquely defined, then the super key of T1 cannot be same as the super key of T2. That means any value on the attribute set that we are considering as a super key cannot have the same value in T1 and T2. So this is the definition of a super key of a relation basis but not as in a functional dependencies. So we will know on in a functional dependencies. Let us consider alpha and beta are two attributes of a relation. Now, if I say that alpha belongs to R and also beta belongs to R because R is the set of attributes and alpha and beta are two attributes. Now, if there exists any functional dependency alpha belongs to B, that means alpha defines B. When alpha for there is a relation R, we need to satisfy it for every beta too. So we can write it like it. So if there is any attribute that has got the same values in two tuples or records, then if alpha belongs to or defines B functional dependency need to be satisfied, then the beta attribute should also be same in the two tuples T1 and T2. So that we can say that alpha defines beta is satisfied in relation R. Now, if alpha defines beta holds on a relation R, then every legal instance that are the conditions that we have mentioned in the previous one, that to be mentioned as a functional dependency on R. So every legal instance can be referred to as T as the legal instances need to satisfy the functional dependencies. So in this way we can say that alpha defines beta is either satisfied or either it is only holding. Now if there is a relation instepped on a particular instructor and department related like this, now we can say that the combination ID and department can uniquely identify the name, salary, building and budget. I am not taking the redundant information into account because I am considering only the functional dependencies here. So the ID and department combination can uniquely identify the other attributes name, salary, building and budget. So we can check for the functional dependencies into two ways. First, we can see that for the values, if the functional dependency is satisfied or not. And in the second way, we can look for that if the functional dependency holds on the relation instead or any other relation R. Now, if we want to satisfy, then we need an information or the examples. Let us look at this example. Now in this relation, we want to check for the functional dependency, that is A to C. We know that the functional dependency exists if there is from A to C, then if the value on the A is for the same tuple goes with the C value. So now check for it using this example. So if we check for this A belongs to C, we can see that there is A1 and A1, for that C1 and C1 is there. For the A2 and A2, there is C2 and C2 there. And for another A3, there belongs to C2. So if it is a repetition of A1, there is also repetition of C values according to that. Now let's look for this dependency as C defines A. Now if we look at that, for C1 we have A1, for C1 we have A1. Till now it is satisfied. For C2 it is A2, for C2 it is A2, but for this C2 it is A3. So if the repetitions of values in an attribute, then should be it for the values in an attribute in A2. Now the condition is not satisfied here, so the dependency is not preserved. As for the B and D, we can look. Now in this two tuples T1 and T2, if we look at the B and C values, that has got the same one. But for this A and D values, we got the different one. So we can say so now the A comma C cannot be a super key to the relation this one, because two tuples has the C value in same but the A value in different. But we can have the B comma C as a super key because it satisfies that for every T1 equals to B, there is T2 equals to C. So we can say that the super key formed including the functional dependency, so that we can form a pair of attribute which is a part of the functional dependency and also following the rule of the super key. Now there are some dependencies which are trivial, that means which are satisfied in every cases. If we take the functional dependency A belongs to A, that means A always satisfy all the attributes of A and it makes it trivial. Also if I say that AB belongs to A, so that a combination of A and B that has a part of A in it on the left and right hand side both will also is a trivial, because for every combination of A and B there will be a corresponding A to it, because the left hand side or the defined part is got an A in it. So we can formally say that if beta is some for part of the alpha, then we can say that alpha defines beta is a trivial functional dependency. Now, we should not keep some type of the functional dependencies, as in real situation it can get changed. Now, if this capacity and room number relation, say in this way we have the functional dependency that the room number defines the capacity. So this preservation of the dependency is absolutely fine for a logical schema. But when it is applied in a physical or a real world application, we can have more than two room numbers which has got the same capacity in it. into different buildings. Say for in building A, room number 101 has 50,000 capacity, and in building B, room number 101 has also got 50,000 capacity. So this makes the redundant information if we keep the building, room number and capacity in a single data or the relation. Now if in the set of the A, B, C attribute, say for an instance a relation R have A, B, C as a set of attributes. Now if there exist of two functional dependencies, that is A defines B as well as B defines C, then we can automatically say that A defines C. So that is known as a transitive functional dependencies. When we form a set of the relation as a set known as F plus of F, so we know this is a closure of F if every functional dependency in relation F is satisfied in the relation F plus. So a closure needs to satisfy all the relations or the functional dependencies that belongs to the relations. So F plus is a closure of F if it satisfies all the functional dependencies of F. Now we will move to our next part, that is a BCNF. We can say that BCNF or Boyce-Codd NF, normal form. What do you mean by normal form? That we are decomposing it into smaller schema in such a way that it preserving functional dependencies in more and more accurate form. So after having a first, second and third normal form, we have the Boyce-Codd normal form. We will reversely go back from the BCNF to the third NF. First, the Boyce-Codd as the inventors of the normal form known as BCNF. So if BCNF and there is alpha and beta or the two attributes on attribute set of relation R, then we can say that if beta belongs to alpha and there exists a relation So if there is a functional dependency alpha belongs to beta and both alpha and beta belongs to the relationship set R of relation small r, then we can say that the relation R is in BCNF if and only if alpha belongs to beta, functional dependency is trivial. That means it is satisfied in all the cases. So if a relation is in BCNF, then all the dependencies must be trivial, that there are no more functional dependencies left between two relations, that one attribute cannot define another attribute in a particular relation if it is in BCNF. And the second one is if also alpha defines beta, then alpha must be the super key of relation R. So the defining relation must be the super key. That means there exists only one or combination of more than one attributes which defines the other attributes because it uniquely identifies the relation. So there exists only the super key concept in BCNF. Other than that, no functional dependencies are preserved in BCNF because every other dependencies are trivial. Now let us look back to our instructor department relation, which has got the ID, name, salary, department, building and budget. Now if we define it and decompose two of the relations, instructor and the student or the department, as in this way, now for satisfying the first one, we can say that if ID is defining name, then it's a trivial one. ID is defining salary, it is also a trivial one because the primary key constraint, and for the department also it is a trivial one. Now for the second one, that ID is the only one to uniquely identify all the other fields or attribute sets in relation instructor. So ID defines name, salary, That means that it is satisfying the second condition too. So it becomes that the relation is in BCNF. Now for the second one, I am dividing it to a department relation, and the department relation got the department name, the building, and the budget. So if I again perform the department name as the primary key, then also we can say that the department name is the one to uniquely identify the building and budget. So the department is the super key of the relation department, and the department and trivial relation dependencies that it uniquely identifies the building and budget. So it is also is in BCNF. So we can say that now we have reached that for instructor and department is in BCNF. Now, other than being in BCNF, we can also decompose it using the functional dependencies. So we are not considering the BCNF for onwards. So if alpha and beta are two attributes from a relation R of relationship set capital R, then we can say we can decompose it in two ways. The first is the union of alpha and beta. That means all the values that has got in alpha as in beta. And the second one is that we are subtracting first we are subtracting the alpha from the beta, and the rest of it we are subtracting for the R. That means we got all the values that is not present in beta which have been in common in alpha, and all the attributes that has got beta in it but not R in it. So we are having that the beta and alpha are two different parts of that union. One is then combination, another is the left around relations. So again for our instructor department, if we make the decompositions like so our alpha union beta will be department name, building and budget. That means and if we go for the second one, that is R minus beta minus alpha. So beta minus alpha is null because beta and alpha both are different. And if we subtract null from the relation R, then we'll get all the relation attributes in R. That forms the instructor. So again, without reaching the conditions to BCNF, we are having the instructor relation as well as the department relation as two lossless decomposition forms. Now, what is to doing with the department and the dependency preservation in BCNF? Well, the dependency is not preserved in any type other than the primary key dependency in BCNF. Let us look at this example first. Let us look at this relation. As we know that a student can have more than one instructor as its advisor, now I am specifying that a student can have more than one advisor or the instructor, but at most one per department. That means from each department the student has got only one advisor. How to denote it in an ERD? We are having three relations: instructor, student and advisor department entities related with the department advice relations. Say there are more students that can be linked with only one advisor from the department. Also, one instructor can be allotted to one instructor at the department. That means there is for a particular department, particular instructor for that student. Now the student can have more than one instructor from other departments, but one department per one instructor. Now how to define this dependency in our relation? Now we are forming an schema department advice from this ERD, that a relationship is formed as a relation which has got the student ID, the instructor ID as well as the department. That means one student, one instructor per each department. So now how to decompose it for the dependency preservation and in BCNF? So if there are two dependencies, first one is there can be one instructor who can be the advisor of one department. Also that if there is a student and has got a department, then there should be one instructor to advise. So one instructor for each of the department, or an instructor can be the advisor of one department only. So say if Kim is the instructor, he can be the advisor of physics department only. And the SIT department, that is the physics and student Wu, can have the Kim as its advisor. So these two functional dependencies are dependent on each other, and we can say that both are deriving on IID. So if we can have a relationship that is recursive from their department, and from their department we can have this IID. So it is just recursive in both the ways. Now, if we converse these two reversations on these dependencies, then we can say that we are actually having the department name both as a combination of an IID department or as a SID department IID. So not necessarily we can have the department name that is being redundant or appear both in the relations because of our decompositions. So the decompositions are dependency preserving but not in BCNF, because the first condition in BCNF is not satisfied, that both dependencies are trivial, because we cannot say that IID is defining the department in its trivial way or in every sense. Now that we are not satisfied in BCNF, but the functional dependencies are preserved, so we need to go into some weaker form than BCNF, which we will say that is in third normal form or the dependency preserving form. So in third normal form, we preserve the functional dependencies, which we cannot do in BCNF. So firstly, we need to keep in mind that BCNF provides a primary key dependency, as well as we have to say that the super key is the only key to define all other attributes. Now in third normal form, additional to it, we have the preservation of functional dependencies. So if there exists a functional dependency alpha defines B in such a way that both alpha is a part of R and beta is a part of R, then if we can say so, now we have all the two conditions from BCNF, and the closure F plus of F is in third normal form if it forms that every attribute A in the beta minus alpha, that it doesn't belong in alpha but belongs to beta, is a candidate key of relation R. That means we are actually preserving the functional dependencies. What do you mean by candidate key? That is a minimal super key. Note that it is not mandatory that from this beta minus alpha, every A should in this as a candidate key. So there should be at least one attribute A that belongs to this beta minus alpha, which is in a different candidate key of R. That there are more than one candidate keys which forms different attributes from beta minus alpha. So the BCNF for the dependency preserving way is providing into 3NF. So when we will see that how to decompose in 3NF, we can actually see further that how to preserve the dependencies while decomposing it into this beta minus alpha, or that alpha preserving on an attribute and a part of a candidate key R. Now, after that the 3NF has been preserving the functional dependency, then we can say we can move to the higher normal forms. The higher normal forms generally deals with the complex and multi-valued attributes. When we talk about multi-valued attributes, that means the attribute can range a domain which has got multiple values. Say for the instance, we are taking an example of a relation. So we have decomposed the child name with the ID and child name's phone number with the ID. Now if we recompose it into a single schema, that we will have ID, child name and the phone number, then we can say that we can have repeated values, and we cannot say that what are the values that were actually meant to. Suppose the combination has got now for the instructor ID, his child name and the phone number has got malicious values. So we cannot say that for 999 ID of the instructor, the David got 543123 contact number, or the David got 6478 contact number, because both the David is working for the instructor ID 999. So this type of decomposition is a loosey decomposition which actually loses the logical part of the data. So we need to decompose it in a more accurate way to achieve the higher normal forms. So now if we can decompose the result of this child name and phone number in such a way so that we can have only a combination that will got the David as 543123 and William as 6478, not this ones, then we can say that we are actually preserving the dependency without being a redundant information to it. So that makes me do on higher normal forms on the BCNF and the 3NF. So that is all for the decomposition using the functional dependencies. Thank you for watching this video. Stay tuned with Ekeeda and subscribe to Ekeeda.